In this video, I'll discuss my recent paper, Diffusiophoresis in the presence of a pH gradient. The work is original and it's part of the special collection Interfacial Active Matter in Physical Review Fluids. It was published in November 2022. The main theme of the study is diffusiophoresis in the presence of pH gradients. We used a microfluidic dead-end pore geometry and synthetic microspheres to investigate the influence of pH change on the particle behavior. To test different signs of the zeta potential, polystyrene and amine-modified polystyrene particles are used. The pH-dependent zeta potential was included in the theoretical model by considering the charge regulation idea. We also noted that the pH gradient changed the surface potential of channel walls and affected the diffusiosmotically induced liquid flow. Now let's look into the details. Diffusiophoresis is the spontaneous motion of colloidal particles under a solute concentration gradient. If a spherical particle with a negative surface potential is located under a simple salt gradient, diffusiosmotic flow is generated along the particle surface down the gradient. Since the particle is mobile, the shear stress will make it move to the opposite direction, and this motion is called diffusiophoresis. The simplest form of the diffusiophoretic velocity formula is the mobility times grad log c. Here, gamma p is the diffusiophoretic mobility that is a function of zeta potential, and c is the concentration of salt. For detailed explanation of diffusiophoresis, please refer to the inserted video on the top right corner. Having diffusiophoresis is considered advantageous for moving micron-sized particles, as the typical particle mobility induced by a simple salt gradient like sodium chloride is 1,000 times higher than the particle's own Stokes-Einstein diffusivity. In this work, we focus on the effect of varying zeta potential on diffusiophoresis. The zeta potential of a surface is a result of complex interaction between the surface and the ions nearby, and the pH of the surrounding liquid is one of the parameters that strongly influence the zeta potential of a surface. By utilizing the dead-end pore geometry, we observe the particle motion along transient pH gradients of various range. Along the narrow pores connected to one side wall of the main channel, a one-dimensional solute gradient can be created. Depending on the initial and boundary conditions, we can entrain particles into the initially empty pore, compact existing particles toward the end of the pore, or move a patch of particles along the solute gradient. One very important feature of the dead-end pore system is that the solute gradient that moves particles also generates the diffusiosmotic flow along the pore walls. This surface flow induces bulk liquid flow inside a pore, and as a result, the apparent particle velocity becomes the sum of the diffusiophoretic velocity and the local flow velocity. I won't go through the details of the liquid flow here, and I'll move on to the pH dependence of diffusiophoresis. Now let's consider the simplest acid and base, hydrogen chloride and sodium hydroxide, and the corresponding diffusiophoretic mobilities at different zeta potential values. For hydrogen chloride, the mobility is positive for positive zeta potentials, whereas for sodium hydroxide, the mobility is positive for negative zeta potentials. Therefore, if we put the negatively charged polystyrene particles under a sodium hydroxide gradient, the particles move up the gradient. We also confirmed that the positively charged amine-modified polystyrene particles move up the gradient of HCl. So far, the sign of the mobility seems to be consistent with the experimental observation. However, if we put the amine-modified polystyrene particles under a positive NaOH gradient, the particles behave similarly to the negatively charged polystyrene particles. We asked if this may be due to the pH-dependent zeta potential of the APS particles, and the zeta potentiometry partially confirmed the question. Between pH 11 and 12, there is sudden sign change of the zeta potential of APS particles, and these pH values are consistent with our test condition. Before we fully analyzed the results from the current setup, we conducted a separate set of experiments examining the diffusiophoretic behavior of APS particles in a wide range of pH gradients. As there is a sign change in the zeta potential of amine-modified polystyrene particles, we designed a new set of experiments to observe the behavior of these particles initially immersed in a 10 millimolar HCl solution and then exposed to concentration gradients created by 1, 3, 5, and 10 millimolar sodium hydroxide. To highlight the front of the particle trajectories while using a finite number of particles, we chose the particle patch configuration. Let's now focus on the behavior of the particle front. When there is 1 millimolar NaOH in the main channel, the APS particles are always positively charged and the direction of motion is always down the pH gradient toward high HCl concentration region. When there is a 10 millimolar NaOH solution in the main channel, the APS particles are initially positively charged but become negatively charged as interdiffusion occurs between NaOH and HCl. Consequently, the particle front changes its direction of motion around halfway along the pore. For the cases with 3 and 5 millimolar sodium hydroxide, the flat particle fronts stop moving near 600 micrometers and then become a parabolic shape. Along with the travel distance, the shape of the particle front is an important feature to point out. In all 4 experiments, the particle front is flat when traveling toward that end. This indicates that the PDMS wall is almost uncharged in the presence of 2 millimolar HCl, and there is no diffusiosmotic flow along the pore walls. We choose this regime where the flat particle front is moving down the pH gradient and analyze the trajectories with a theoretical model. To accurately predict the particle front behavior in the patch experiment, we used the multi-ion diffusiophoresis model with a pH-dependent zeta potential. The charge neutrality and the zero current conditions hold, and the formula for the diffusiophoretic velocity now includes interactions among all ions and the zeta potential of the particle surface. We consider the charge regulation model for the pH-dependent zeta potential. For commercial polystyrene particles, their surface is often treated with sulfate, carboxylate, or amine groups. Since the extent of proton binding to these functional groups at different pH directly affects the surface charge density, we can calculate it by considering the acid-base reaction kinetics and the Boltzmann distribution of ions. For the amine-modified polystyrene particles used in this project, the surface has both the sulfate and amine groups. So, by using the number density of these groups and the pKb value as the feeding parameters, we can get a nice curve that represents the pH-dependent zeta potential of the APS particles. For direct comparison between the experiments and model, we measured the particle front trajectories from the chymographs and calculated the one-dimensional trajectories using the matching initial position of the particles. Such a one-dimensional calculation is sufficient for this comparison because the particle front is flat and there is no influence of the diffusiosmotically induced flow. By using the pH-dependent zeta potential obtained from the previous slide, the particle front trajectories were accurately predicted without additional fitting parameters. This comparison indeed confirms the pH dependence in the diffusiophoresis of APS particles. Now, knowing the sign change behavior in the zeta potential of APS particles between pH 11 and 12, and knowing the occurrence of the pH-dependent diffusiophoresis, we are back to our initial experiment. Is it enough to explain the behavior of APS particles under this NaOH gradient in the compaction configuration? Since the compaction boundary is not flat but parabolic, we must think about the influence of the wall diffusiosmosis before reaching a conclusion. To test different combinations of the influences of wall diffusiosmosis and APS diffusiophoresis, we designed another set of experiments testing various pH gradients created above pH 7. We chose the combinations of sodium chloride and sodium hydroxide and controlled the ionic strengths to be 2 millimolar in the main channel and initially 20 millimolar in the pore. As a result, the APS particles are always positively charged in the condition 1 and always negatively charged in the condition 4. The surface potential changes its sign in the conditions 2 and 3. As shown in the pictures, we observed different compaction behaviors of the particles that were initially filling the pores. The main feature to remember in these experiments is that the APS particles moved up the gradient in all 4 conditions, regardless of the pH-dependent sign change of the zeta potentials. Similar to the earlier particle patch experiments, we tried to predict the directionality using the pH-dependent zeta potential and the one-dimensional particle trajectory. However, this calculation failed to predict the compaction behaviors of the APS particles. Unlike the particle patch experiment where the front shape was flat, the compaction boundaries in the current experiment are all parabolic. This means that the influence of the wall diffusiosmosis-driven flow is not negligible, and we must include the flow effect in calculating the particle trajectories. To accurately include the effect of diffusiosmotic velocity, we consider the pH-dependent zeta potential of PDMS walls. The correct comparison is now shown in the new plot. Only after setting the particle velocity as the sum of the pH-dependent diffusiophoretic velocity and the local flow velocity, the direction and magnitude of the transport is accurately predicted. Therefore, it turns out that the very initial experiment where the APS particles compacted along the positive gradient of sodium hydroxide is an outcome of the combined pH-dependent zeta potential, multi-ion diffusiophoresis, and the diffusiosmotically induced liquid flow inside the pore. Finally, we conduct a thought experiment or a numerical experiment by considering the particles with different isoelectric points. These 3 curves represent 3 different particles with different zeta potential functions of pH. If these particles are put under a concentration gradient of sodium chloride, the diffusiophoretic trajectories will look like the solid lines, and the trajectories that include both the effects of diffusiophoresis and diffusiosmotically induced liquid flow inside a pore will look like the dotted lines. Since the sodium chloride solution is pH 7, we focus on the particle with the isoelectric point 7. This particle will be always uncharged in the sodium chloride solution, meaning that the diffusiophoretic velocity is 0. However, the dotted line tells us that if the pore wall is negatively charged, the particle can still move into the pore by the diffusiosmotically induced liquid flow, and the typical velocity scale of this advection will be the same as the typical diffusiophoretic velocity set by the same salt gradient and the same zeta potential. Therefore, we suggest that it is important to correctly estimate the diffusiophoretic transport and diffusiosmotically induced liquid flow, as we are never free of the wall diffusiosmosis in an experimental system designed for diffusiophoresis, and the pH-dependent zeta potential is a common feature of such system elements. In my previous video clipped on the top right corner, I had discussed the 3-dimensional flow effect inside a dead-end pore geometry. And in the current study, I investigated the pH-dependent diffusiophoresis both in the absence and presence of the diffusiosmotically induced liquid flow. By doing so, I tried to demonstrate the complex nature of diffusiophoresis as a physico-chemical hydrodynamic phenomenon. Before concluding the video, I would like to leave a remark about this feature of diffusiophoresis. Diffusiophoresis is motion of particles relative to the surrounding liquid, and it is induced by the generation of a surface flow. Scientists are actively investigating the phenomenon by focusing on various particle types and various flow configurations with both theoretical and experimental approaches. No matter what particle is used and no matter how the flow condition is set up in the project, the very fundamental aspect of diffusiophoresis, which is the surface flow-driven phenomenon in the presence of flow, must be carried along in the research. In this way, we can avoid misclaiming any apparent enhanced motion as diffusiophoresis, and we can prevent confusing fellow scientists and general audiences with false information. To conclude, we investigated diffusiophoresis of synthetic microspheres under various pH gradients experimentally and theoretically. The apparent behaviors of APS particles tell us that the directional motion of a particle under a pH gradient can be a combined result of pH-dependent diffusiophoresis and diffusio-osmotically induced liquid flow. Again, as diffusiophoresis is a physico-chemical hydrodynamic phenomenon, it is important to ensure that this fundamental aspect is not overlooked when tracking particle motion. Thank you for watching this video, and please let me know if you have any questions about this study.